So our next speaker is Dr. Heike RIEL from IBM, and she will speak about the future of computing from bits to qubits. Heike, maybe Gabriel, okay, perfect. I think there.
I took over. Hello, good afternoon.
Good
late afternoon.
Please, over to you, Heike. Thank you very much for being with us.
Okay, thank you very much, Francesco, for having me. I really appreciate. I would have loved to really come there in person. And since I had a quick look this morning at my agenda and seeing also, you know, the speaker before, I thought I may focus a bit more on the quantum computing part, also through the limited time. But I wanted to start out by the question, the big question, which not only Intel, but also IBM and everyone in the semiconductor technology area is kind of coping with, is the question of what is next in computing. And there are different answers, because in order to increase the performance, in order to increase the efficiency of the workloads which we have, we are so diverse, we can no longer stick with a general processor, but we have to optimize processors for the task at hand in order to squeeze out more energy efficiency and more performance. And this is, I think, a general trend which has been coming up over the last couple of years, but this makes it also very, very exciting to be in computation, also from the hardware development side. And that's actually my background. So when you look at computing, I mean, you are all very, very familiar with high performance computing from the user side. And that's your kind of daily business. And as you have seen before, also by Intel, there is a very, very big scientific community who is actually developing new types of hardware for artificial intelligence to cope with the big workloads, to cope with the big data, and to cope with these complex neural networks, which are increasing and getting more and more complex. As you all seen, ChatGPT has come out. You may have looked also at the energy consumption, the training needs, which I think is more than 1.2 gigawatt hours. So it's a lot of energy, and this is in the end it can only hold if we make better hardware, which is more energy efficient, that also the neuromorphic and the AI can develop even better, and we can afford it from a cost and an energy perspective. So all this computation is delivered through the cloud to everyone, and this will continue to happen. And there is another kid on the block, which is actually quantum computing. And so before I thought I'd talk also a bit more about what do we do, what devices we are building, and how do we squeeze out more of the semiconductor area. And the next step is what the speaker before has mentioned about artificial intelligence specific hardware. And also here we build up a full roadmap with different technologies, from approximate computing to analog computing, in order to increase the energy efficiency. And quantum computing, as I mentioned, is a new kid on the block. And I decided now, since a limited time, to continue focusing on the quantum computation and what we as IBM are doing in that space. Quantum computers has been quite a history already. The original idea was from the early 80s by Richard Feynman. And the idea here was to develop quantum computers, to develop a new types of computer which can cope with the complexity of nature. We know that nature is based on quantum physics, with a lot of multi-body problems, with numerous big equations, and therefore develop quantum computers. But it took a long time to come to a range where we have, as an experiment from the theoretical side, proven the concept, established the concept, and on the experimental side, we're able to build those things. And about 7 years ago, we have brought the first quantum computer online, available through the cloud to everyone. And of course, quantum computers are still in its early phase, but there is a lot of technical progress which is currently happening. And this is what I would like to talk to you about. Not only the hardware progress, but also the progress which is actually happening also on the algorithmic side. So when we look at starting 7 years ago with the first computer on the cloud, meanwhile, we have more than 26 of those systems deployed with different numbers of qubits. I will talk to that about later. There are also, we establishing a community of researchers and of developers to work on quantum computing together in an open space, which is an open software platform also, and to share their experience and to share also and develop together the Qiskit. So we have more than 460,000 users on those platforms. And we are also establishing a network. And I think hopefully many of you have been also participating in that and using our computers through the collaboration we have with Witwatersrand University, now at Stellenbosch, and also soon to come with the HPC Center. So there's lots of activity. The number of daily executions of those quantum computers is rising. And also which I think is great to see that a lot of people are using them, but they are also producing really very valuable output, scientific and technical output, which is published and shared with others, that they can all learn and accelerate the progress and the advancement of quantum computation. So I want to right away show that we are also building on a second system. So you have seen before IBM Quantum System 1, and we are building currently, as I speak, IBM Quantum System 2, which is to be released end of this year. And it's this is a design picture. This is bigger. It actually is a modular system. So you see different chambers which can be, which are modular and can be put together. And this will allow us, the system, to actually scale further up quantum computing, the number of qubits, the control, and everything it needs to run them. So now let me focus a few minutes on why are those quantum computers important. And you all know that there are still many difficult mathematical problems which we only can solve approximately. The speaker before has talked about optimization problems. And so with quantum computers, we hope that we can solve those complex problems in a much better way than classical computers can do, or the hardware which we have for artificial intelligence today. So the 4 classes which people currently investigate to be where quantum computers have the potential to be better in the future are simulating nature, mathematics and processing data with complex structure, and also search and optimization problems. And when you look from an application side, and you have talked before today in the workshop already about a variety of different applications, also for quantum computing, you can find these complex problems, of course, it's many different industries, whether this is from the aerospace and automotive to financial services, high tech, energy, telco, environment and utilities, healthcare and life sciences, etc., etc. So I don't want to go into detail here, but this gives you an understanding that this is really a broad application space, not only from a research and technical side, but also from an industrial relevance side, if we can prove that quantum computers are better than anything which we have today on the classical side. So the question, however, for our researchers and for technologists and for anyone who wants to use a computer is, how do I measure the performance? Because in the end, I care about the result, how scalable the technology is, which means here the number of qubits, what the quality of the calculation is I get out, about, in this case of quantum computing, about circuit fidelity and quantum volume. And the third one is the speed. So how fast do I have the result? So all these 3 parameters are defined to measure the performance. And just so you're aware, measuring the performance of quantum computers is something which has been developing over the last couple of years, how to benchmark also different quantum computers against each other. And you for HPC, you have the famous LINPACK system, but it's really about figuring out what is the right benchmark. And we have contributed in this part on the research and technology in order to measure this. And we came up with the scale, quality, and speed, these 3 measures to be able to compare on a solid ground different types of quantum computation. So let me now focus on scale. because it's important to build quantum processor with large number of qubits in the end. And so it's a technological thing which we have to develop. And you see here flowing over many different quantum processors which we have developed over the last couple of years, starting from the 5-qubit processor, which we have been bringing online in 2016, to the Falcon processor with 27 qubits in 2019, the Hummingbird with 65 qubits in 2020. In 2022, we have demonstrated for the first time a quantum processor with more than 100 qubits in a chip, which was quite a technical breakthrough because you need to go 3D, as I will show you in a second. And also, just last year in November, we have released the Osprey quantum processor with already 433 qubits. So the Osprey, as well as the Eagle, for the first time we had to go 3D in order to be able to really connect all these qubits and make them work together. So you see here different levels of technology in such a chip. The qubit layer, here you see the interconnect layer, and the other layer was the resonator layer, which is important for making the qubits work. So all this had to be developed, and this is just one example to illustrate the complexity and the technical difficulty and problems you have to solve in order to scale up this technology. And this, of course, under the constraint that we have to continuously also improve the quality of the quantum bits. So here you see again the 3D image where you see again here the qubit layer. I'm not sure whether you can see my mouse, but I use it. So the top layer is the qubit layer. Then you have the readout layer with the resonators. And then you have the wiring layer, and then you have to package this that you can also cool it down to about 10 millikelvin. On the right-hand side, you see the connectivity map, which means that every of these white cycles illustrates a qubit. And you see here how they are connected with each other. You have always like of 2 nearest neighbors or 3 nearest neighbors, and we call this the heavy hex network. So by scaling up, there are other technologies to think about what we need to improve, because we all know this wonderful picture of this golden chandelier. You also see these very bulky wires which are going down in order to control the qubits. And these are actually too bulky for scaling up, which means that we had to build actually a new technology, as this is limiting to the scaling of the number of qubits and their control. So on the next chart, you see what we did. We actually replaced these nice and shiny wires through these flex cables, which you see here. And thus we're able now to control a huge amount of more qubits by a new technology and at a much denser, it doesn't need as much volume, etc. So this is just one example. Another example is how to control the qubits. You need electronics. And when we started in 2016, we had 5 qubits in our processor, and it needed a full rack of electronics to control it, which you see on the left-hand side at the bottom. So this is very costly, and it takes energy, and it also needs space. So the next generation of electronics, which we developed, was able to control 20 qubits, and it needed a rack for this. So similar dimension. And we continued to go to generation 2 electronics, where we now can where we could control 40 qubits with electronics, which does not even need a full rack. And you can imagine for the last year, we demonstrated a new type of electronics, where we have where we can control 400 qubits with only a part of an electronic rack. And this, of course, is much more energy efficient, less costly, and this is all needed in order to scale up the technology. So now let's move on and talk about quality. Because quality is very, very important in order to improve the quality of the computation and, of course, the usefulness of the quantum computation to the user. And this one part of this, the quantum volume or quality of a computation, depends on many different parameters, and I don't have time to go into too much detail, but one important parameter is the coherence time. And over many years, the community has been able to further increase the coherence time. And we have also over the last couple of years increased it from around 40, 50 microseconds to now more than 600 microseconds in our test devices. And in the Falcon R8, which is a 27-qubit chip, to around 300 to 400 microseconds. And in test devices, we even reach milliseconds. So you see, there is a 3 times increase for the processors and a 6 to 10 time decrease on test devices, which we're implementing currently in our quantum processors. Another parameter for the quality is the 2-qubit gate fidelity. So this means how much error do you produce when you apply quantum gates to your qubit. And this is very, very important. And you also see here that with time, which is there's a lower scale, the X scale, and the error rate is the Y scale. We are going to the right direction. This is a logarithmic plot to reduce the error rate on our processors. And we have reached now about 10 to the minus 8 times 10 to the minus 3, and we want to reach about 10 to the minus 4 till the next quantum processor stage, end of this year. This is important, of course, for error correction, error mitigation, and all the quality of the calculation which we require. Another important parameter is also the speed, because you cannot wait forever on your calculation, and you want to use the power of quantum computation, so you need to also have a fast speed. And speed does not only depend on the quantum computer, but also on the architecture, because you always need a classical computer to interact with a quantum computer. So when you look at a quantum computer, then there are many different physical implementations, and there are ones which are slow, but there are ones which are fast. And we are using quantum or superconducting qubits, and they have the advantage that they're actually intrinsically also fast. And then by further optimizing also the classical the architecture with the classical computation through the cloud and everything, we can then improve also the speed of the computation. And this, of course, has also a lot of parameters which are relevant for the speed of the computation, like code pipelining, the control systems, the compiler, the quantum engine, and a lot of different things. And we were able, as you see here in this plot, last year to achieve quite some boost, and we're able to reach about 15,700 clops. And clops is a circuit layer operations per second. And this is a metric which we have defined and published like 2 years ago. It uses a certain algorithm, and I can refer you to the publication for more details. So now let's see what's coming, or let's first start, okay, what have we demonstrated since 2019, which is actually indicated here. We have laid out a roadmap starting in 2019 to kind of predict and what we want to demonstrate in which year. And so we have till end of last year very nicely also demonstrated what we promised to deliver, as you can see here on the bottom on the hardware side. First with the 27-qubit Hummingbird, Eagle, and Osprey. And then we are also building up the software level to make it very easy for you to use quantum computers, as you may not so much interested in worrying about the details of the hardware. So therefore, we are defining actually 3 levels of software developers. One is the kernel developer. The kernel developer needs to understand the hardware because he defines that or determines and sets the tools for the software to interact with the hardware. And the tools which are developed by the kernel developer are then used by the algorithm developer to implement new types of algorithms. And the one on top, the model developer, actually then trying to solve a problem by being able to use the tools of the algorithm developer. So he does need to know not a lot about the specific hardware. And that's something which we are developing. We have started already in 2019 to develop like also application modules, which make it easy for users to solve typical quantum problems in the area of chemistry, nature, optimization, and also machine learning. And so what's coming next? Again, we have these different levels on the software side, but also on the hardware side. And on the hardware side, you will see here that we are developing a new type of scaling up for quantum processors. We will demonstrate first a full chip with more than 1,000 qubits end of this year. And we will also start, or we have started also to develop a modular approach. And that's a bit similar to what you know from the HPC area, where you also use and parallelize your job and then compute it on many different classical processes and then bring the solution together afterwards. And so this first approach is a bit similar. We will connect different quantum processors with a classical communication line with a universal bus and controller. And these individual quantum processors can also interact within the coherence time of each other. The next step, and so there are also different software tools which we're developing on top. I perhaps talk about this later. So let me then go to the Flamingo, because next year we will then utilize these capabilities of combining different types of quantum processors with classical links, but also with quantum links to scale up the number of qubits in those processors. And Grossbill, the one with 408 qubits, is actually a chip which uses, which is based again on a modular approach, but it uses, instead of classical links, quantum communication links to communicate between different qubit processors. So we will use here like, so in the end, this chip actually looks to you like a big single quantum processor to the user, although it consists of a certain number of individual quantum processors. And these type of linking classical linking quantum processors with quantum links and with classical links allows us really to scale up in the future in a much better way the number of qubits. And in 2025, we want to reach, we want to build the so-called Kookaburra quantum processor with more than 4,100 qubits. So you see, there's quite a lot of technology being developed, and from the hardware side, but also on the software side, you see on top that there are quite a few things. So there are different software features or capabilities which we are developing to make it easy for the user to then apply them and employ them in their computation. And there are dynamic circuits. Dynamic circuits, I don't have time to go into too much detail, but they will allow you to actually talk with the different quantum processors within the coherence time. This means you can, depending on the flow of your computation and the result, you can make then changes to your program. And this will allow that you can solve problems with a much shorter depth. This means number of gates than you would need if you don't have that capability. Then threaded primitives, that's about really using these parallel quantum processors. And another very important point is also the error suppression and error mitigation technique. And then finally, 2026, where of course, it's getting a bit more blurred because we will define this more specifically the more we develop and know and can be more precise in our prediction. But here we are thinking already now about how can we scale this up, of course, to much larger number of qubits, which then allow also error correction in the end. So let me now finish our talk a bit about error suppression and mitigation, because it's a very important topic and these capabilities are coming up with our quantum computers for you to use directly. So why quantum mitigation? So as you know, the quantum error correction needs quite an overhead, but it provides you then in the end a advantage to the classical computer, which is proven. So what you see here is actually a chart where I have indicated the simulation cost on the y-axis and the quantum circuit complexity on the x-axis. And when you choose a problem where a classical computer has an exponential cost involved, then we know that, for example, for Shaw's algorithm, that there is a quantum error correction. When you have quantum error correction, then there is the evidence and the proof that with a quantum computer, you can solve some of these problems with less cost. And this is actually why, of course, they are so much interested. But you also see that the circuit complexity, it needs quite a lot of overhead. And what we want to do is we actually think that there is not a step function to go from a classical one to a quantum error corrected one to get value, but that you get value out of quantum computation, hopefully already by using quantum error mitigation. This means that today we are here actually where we are not able yet to show quantum advantage, but by error mitigation, we believe that with less overhead than classical computation, we can solve a problem. And this would then be really utilizing the sweet spot area here for quantum error mitigation. So what is the quantum error mitigation? And here I just want to give you an example. This is an example of a quantum computation we have already done in 2017, a very simple one, calculating lithium hydride. And you see the green solid line is a correct answer simulated by a classical computer, and the dots here show what a quantum computer has been done. And at that point, the errors were kind of masking the result and leading to this error. So when you actually do error mitigation, which means you understand the error, you naturally increase your pulse widths on the how you do your calculation. I mean, it goes a bit into too much detail. I'm sorry about that. But this means you increase your error intentionally. And by doing this, you can actually then you amplify your noise, and you can then scale down to zero noise. And this gives you the correct result. And we have shown in 2019 that with this error mitigation, which is shown here, we have more overhead. We have to do, like, instead of one calculation, five calculations, but we can then get the exact result. And this is currently what we are working on to apply this technique also to the large qubit processors. And I can't talk today, but we have promising results, and stay tuned for a publication to come out. Because when you have processors with more than 100 qubits, you're no longer able to actually calculate it classically. So then you are beyond this, you cannot calculate this green line then classically anymore when you deal with problems which need 127 or over 100 qubits. And that's one really promising development which we're working on. And the other one I want to highlight is the circuit knitting toolbox. And circuit knitting is indicating or coming back to what I mentioned before. We are creating this parallelized quantum processors because there are applications for it. And this is called circuit knitting, where you combine quantum and classical. And in simply spoken, you kind of cut your big problems into different smaller problems, and then you solve these smaller problems on the hardware which is available today, and you find ways of how to stitch it then together to get your solution. And there are many different approaches. I don't want to go into detail. One is embedding. Here you effectively leverage the QBU resources. You only solve the part of the problem which mostly benefits of the or which has the highest entanglement and benefits of the quantum processor most, and you solve the rest with the CPU and then bring the solution together. And so there are other techniques also, like entanglement forging or circuit cutting. And these are techniques which are currently explored. You see the references here, and they're also very, very promising to be used then for the modular approach, which we are coming up end of the year. And these tools are also or they're already in an alpha version part of our Qiskit, and they will come up soon and in improved versions. So I think let me skip this. I just want to highlight also that we are developing Qiskit, which is an open source software kit for quantum computation, and we are building a large range of tools that you as a user in the HPC community can use and run quantum programs. And so here are some. We have developed applications for high-level applications like Qiskit Nature for finance, for optimization, for machine learning. And there are also different, there's a simulator also available, but also core capabilities where you can also influence the pulse shaping, where you can go deeper into the hardware and work with the hardware. And actually, a Qiskit is also hardware agnostic, so you can also work on ion type of quantum computers with AQT and IonQ. So Qiskit then enables you to use a wide range of tools to build quantum programs. This means you start out by building your circuit, to then define a task, and you can prepare and the program and execute it on the quantum hardware. So, however, for achieving quantum advantage, you always need also the interaction with the classical hardware. And again, we also want to make this very, very simple and orchestrate this in the middleware. And so that's something which is currently built, because you need to optimize as a user concerning accuracy, cost, and time. And we are currently building the tools out for you to allow this. So we build a full middleware for quantum set with a decomposition of the tools for circuit knitting, the intelligent orchestration toolkit for quantum serverless, that you don't need to worry about the resources you may need concerning classical AI and quantum. And this is all delivered in Qiskit runtime, and make it then easy for you to use. And yeah, that's how we believe and how we envision and what we work on to develop all these tools for you to easily use. So I want to close, actually, I'm sorry for a bit of a delay, but I want to close here by some challenge which we have set for ourselves, but also set for the community for this year. And we are building currently a hardware capability which allows the user to estimate noise-free observables of circuits which consist of 100 qubits and a depth of 100. And all this done within a day. So this, is really a compute capability which you can utilize for a certain problem. And so the question now is, what is the problem you can map to this 100 times 100 challenge in order to perhaps get a quantum advantage? So we actually asked the entire community to think about relying on next year, there is this capability of 100 times 100. So again, a number of qubits of 100, a depth of 100, and all this calculated within a day. And what is the problem you can think of to map to this capability and achieve quantum advantage? This would be fantastic. So with this, I actually want to, let me see, go to, so yeah, kind of this maps it or illustrates it again. So you have 100 qubits, which you can use in parallel, and also apply 100 unitary metrics, and then be able to measure, and all this done within a day. And I hope you can come up with a cool problem to be solved on this capability. So there is a lot of education and workforce enablement. I hope we have a team also in Johannesburg, and they're also organizing a lot of Qiskit workshops, meetups, summer schools, etc., etc. I hope some of you may have been part of it. And we are also joining forces with the team here to make this an even more growing and agile community as it already is. So with this, I thank you very much for having me. Thank you very much.